Hello, my name is Silvia Elena Nistor, and I am here today to talk about real-time scheduling in drop computing. The growing popularity of mobile devices in the 21st century and the diversity of their architecture and purpose has triggered the genesis of one of the most popular and promising technologies known worldwide under the name of Internet of Things. Billions of physical devices are connected to the Internet and communicate real-time data without human involvement, creating a transparent fabric surrounding the world and agglutinating the physical realm. Smart homes, self-driving cars, smart cities, surveillance systems, face recognition, all upgraded the world we once knew by merging multiple technologies and adding sensors and intelligence to regular mundane objects that are now indispensable components in our lives. The Internet of Things has irreversibly imprinted on almost any imaginable aspect of human life and expanded tremendously to the point where computation intensive applications, limited resource devices, and continuous need of reliable interconnectivity have put an enormous pressure upon the quality of experience and service. Users' expectations increase gradually, focusing on aspects such as power consumption rate, speed, security, scalability, and availability. The traditional approach, which is universally approved and embraced, consists of cloud computing. The vision encompasses a paradigm shift on data processing and storage remotely, away from the local resources on data centers located across the network. Cloud computing made an undeniable breakthrough in processing and managing big data, but the model still faces concerning limitations, mostly regarding latency, security, and privacy. The centralized data center model proposed by the cloud acts as a single point of failure and cannot scale enough in the face of the big data volume. Therefore, the vertical scaling of cloud infrastructure is slowly complemented by the horizontal approach with a greater focus on decentralized paradigms. In the light of these shortcomings, numerous alternatives were proposed in order to fill in the gaps between the cloud and the Internet of Things, such as edge, mobile edge, and fog computing. Edge computing proposes data processing in the proximity of data sources by allowing computation to be performed at the edge of the network. The term edge defines any resource with computational capabilities found on the path between the data source and the cloud servers. The basic idea is that devices collect data from the surroundings and perform the computations locally and only offload work to cloud when there is no other option. The cloud resources are still available to do the heavy lifting, but the number of accesses to over the network data centers is significantly reduced. Regarding the security aspect, data is contained closer to the source without being sent over the internet, which is a great security improvement compared to cloud solutions. Mobile edge computing aims at reducing network overhead by leveraging mobile devices' resources. Technological evolution led to the proliferation of mobile devices, which require, of course, mobile applications. However, in this scenario, the data processing is highly dependent and limited by battery capacity and power consumption. Mobile edge computing provides computing capabilities at the edge of the cellular network, closer to mobile subscribers, on base stations, central offices, or other aggregation points on the network. Fog computing reduces the reliance on cloud-based platforms by using capabilities um, from any processor connected to the same local area network. So the only difference from edge computing consists of where the data processing takes place. However, all of these models still rely on the client-server model, which might be overwhelmed by the huge influx of data in the future. Drop computing aims to address this concern by proposing a decentralized model over ad hoc dynamic networks. This architecture is based on two existing models, cloud computing and opportunistic networks, while also adding a social crowd component. In drop computing, devices can borrow resources from geographically collocated nodes. Thus, any device is viewed as a potential cloud resource. The computations are divided into fine-grained tasks and offloaded to available neighbors through wireless technologies. This way, a grid-like platform is created where devices create social connections and human-like ties, collaborate and extend their local resources, crossing the local hardware-imposed barriers. Besides reducing the traffic towards the cloud and the exposure of data to the internet, the major advantage of this new paradigm are operational cost reduction, horizontal scales, um, and battery power preservation. The applications on a certain device participating in a drop computing network are called droplets, hence the source of inspiration for the paradigm name. Because these droplets are then offloaded on other nodes for computation aid, the overall system performance highly depends on the scheduling policies and strategies adopted by each machine. In our research, we focused on the task scheduling aspect of drop computing because we wanted to optimize the opportunistic communication, to calibrate the system resource, and to reduce unbalanced workloads, thus improving the system performance. We took the analysis one step further and concentrated our attention even more specific on the real-time dimension of the tasks in the context of social dimension. The users cannot apprehend the world without instant messaging, video streaming, or online gaming, so we chose to adapt the implemented scheduling policies for the real-time tasks and observe the results. In such a decentralized system, there is a high chance of disproportion between nodes' load. Some nodes can be selfish or unwilling to participate in helping other nodes, or too altruistic, thus overloading themselves with too many tasks. We consider this to be a second dimension to our scheduling analysis. On one hand, we can refer to local scheduling, which translates into fair and efficient resource allocation between tasks on one node, but on the other hand to global scheduling, which preoccupies with the welfare of the whole systems through balancing the task allocation between nodes. Therefore, our objectives resume to analyzing the system behavior and overall performance when applying different scheduling strategies at a local and at a global level, while also considering the case of real-time tasks and how the nodes should react when encountering them. Real-time integration gives us the sense of live participation and interaction with multiple instances and breaks the geographical constraints in communication, which is why it has become a crucial component in current technologies. In the following part, I will talk about our implementation model. When discussing real-time tasks, they can be divided into three categories. Critical tasks, the task must be completed before the deadline under any circumstances. Essential tasks, the tasks can exceed the deadline but the performance will be seriously damaged. And non-essential tasks, the deadline can be surpassed without any serious concerns. In our research, we assumed having critical and essential tasks, with a clear need of defining a set of rules for respecting the deadlines. These tasks will always have priority in execution. They are always dropped when the time expires, and if the task is lost, there is no retransmission. We chose a set of popular local scheduling algorithms: earliest due date, first come first served, last come first served, round robin, and priority based round robin, using a sorting queue and comparators. In the real-time case, the comparators prioritize deadline constraint tasks. For the global scheduling, we implemented two components called Publisher and Balancer. The Publisher component gives an overview of the social network at a certain moment of time in the simulation, with information regarding each node's available resources. After a device receives the list of eligible nodes for task processing, the balancer performs task exchange between two encountering nodes if they are unbalanced. The simulation environment that we used is MoBEMU, Mobility Emulator, an opportunistic network simulator based on home cell mobility model, which monitors both the interaction of the nodes and their geographical movement. It contains detailed definitions for nodes and devices, for the system parameters and their tasks. We added support for three types of tasks: small, medium, large, in order to include CPU and I/O intensive jobs. The real-time tasks are randomly generated from the small and large categories, and we also added a limitation for the maximum number of task groups in our simulation. We added the class system that adds information about the CPU and RAM usage. Our tests were conducted on a 9-hour simulation with 20 nodes grouped on a 200 by 200 meter area, partitioned into 20 by 20 cells, through which each node travels at a speed between 0.25 and 1 meter per second. We envisioned a use case for a community of teachers working for a research subject, exchanging data and test results. For the system parameters, we configured nodes similar to iPhone 7 specifications, and we studied all possible combinations of local scheduler, publisher, and balancer with and without the real-time case scenario to analyze the changes in the system results when prioritizing the real-time tasks. The first half of our tests were done without using the cloud, and in the second part, we also involved the cloud for computation. The sets of tests are available at these links if you are interested in having a better understanding of how we conducted our tests. Now, let's discuss each local scheduling policy and analyze its efficiency when combined with different global scheduling strategies. We have extracted the average battery decrease rate, the average tasks completion rate, and the average real-time task completion rate. We also introduced the limitation for maximum task groups generated by each node ranging from 2 to 2048. However, on this presentation, we chose to get the average result from 512, 1024, 2048 maximum task groups, because for lower values, the results weren't that helpful for a relevant comparison. For the earliest due date algorithm, we can observe that the average real-time task completion rate was highly improved when adopting our real-time comparator to prioritize these tasks. On the other side, results were unfavorable when using the default strategy. In the first come first served case, the behavior is similar to the earliest due date case, meaning that the real-time comparator drastically improved the real-time task completion rate. Again, using a default comparator, or even worse when involving the cloud, the completion rate worsens. However, in any case, this algorithm has better results than earliest due date. The next algorithm is last come first served, which again has satisfactory results when using the real-time optimization, but the cloud involvement delivers poor performance. When discussing round-robin algorithms, we must first choose a quanta. For this presentation, we will show the results for a quanta of 300 milliseconds. The default round-robin algorithm worked really well with our optimizations, both for the local scheduling and for the global scheduling for real-time. Again, the cloud involvement had a negative impact on the completion rate. For the priority-based round-robin, the test considered a 350 millisecond quanta. We can see here that this algorithm offered encouraging results with high real-time task completion rate in almost any combination used without the cloud. In conclusion, the cloud had a negative impact on real-time task completion rate because the deadline for the tasks was not met. Moreover, it was our goal to optimize the drop computing algorithm for the real-time scenario, and we can observe a great improvement whenever we choose to use the optimizations. In general, prioritizing real-time tasks at a local node has proven more effective for the completion rate than at a global level. Overall, the round-robin based algorithms deliver the best results, while the earliest due date algorithm had the lowest values, lower than 0.5 completion rate in some cases. The results are satisfactory, proving that with the right scheduling policies, deadline-restricted tasks can be more efficiently computed and further work can be pursued in this direction. Thank you for your attention.